Hello everyone, and thank you for attending this talk. I'm excited to present our work titled, Multirate Neural Image Compression with Adaptive Lattice Vector Quantization. Let's begin with a brief background. Neural image compression typically involves, for steps, an analysis transform converts an image into its latent representation, quantizing the latent features, entropy coding of quantized latent features, and a synthesis transform reconstructs the image. Recent progress has focused mostly on improving entropy models, while improving quantization remains underexplored. Scalar quantization, or SQ, is widely used because of its simplicity. Vector quantization, or VQ, is theoretically optimal, but has high encoding complexity and unstable training. Lattice vector quantization, LVQ, offers a compromise, with better structure than SQ, and much lower complexity than conventional VQ. Here's a visual comparison of different quantizers. From left to right, we see a general VQ, a scalar quantizer, and two types of lattice quantizers. Compared to SQ, LVQ provides better space-filling efficiency and captures interdimensional correlations. LVQ can achieve smaller quantization error than SQ at comparable rate. Compared to traditional VQ, LVQ has a mathematical structure that enables fast encoding and does not require the storage of codebook. Formally, LVQ defines the quantized vector as y hat equals b multiplies u, where u is an integer vector and b is the lattice basis. The output of LVQ is defined as the integer linear combination of lattice basis. This structured layout can eliminate the need to explicitly store a codebook. More importantly, when the lattice basis are some specifical basis, the corresponding LVQ has fast quantization algorithm. Let's take the diamond lattice as an example. It can be constructed by combining a square lattice and its cassette, a shifted version. This structure allows a fast quantization algorithm. We simply round the input to two candidates, one on the black, square, lattice, and one on the red, shifted, lattice, then select the closer one. This efficient quantization avoids dense nearest neighbor search and makes LVQ highly practical for deployment. Now let's look at our method. We start by identifying two main limitations of existing LVQ-based compression schemes. They do not support variable bitrate control, and they are not adaptive to different data distributions. We address both issues with a unified LVQ framework. In our design, we maintain a bank of lattice quantizers. Each quantizer corresponds to a different scaling of the lattice basis B, allowing rate adaptation by controlling the density of lattice points. In parallel, we enable domain adaptation by applying a set of learned linear transform to the lattice basis. Each learned linear transform can reshape the Verneuil cells and allows the quantizer to better fit the data distribution of target domain without modifying the neural encoder decoder itself. Now let's take a look at the experimental results. On the left, we show rate distortion, RD, curves on the Kodak and click datasets. We compare for versions of the Cheng 2020 baseline, 2 with scalar quantization and 2 with our proposed LVQ, both in single rate and multirate settings. You can see that LVQM, our multirate version, consistently outperforms the scalar quantized baselines, especially at low bitrates. On the right is a table showing domain adaptation results. Here, we evaluate models whose quantizers are adapted to the SCI1K and the PAX cartoon dataset. Again, our LVQ-based model shows consistent gains in BD rate, and BD-PSN are across all categories, without modifying any network components. In future work, we aim to further improve the effectiveness of LVQ-based domain adaptation to achieve greater gains. We also show visual comparisons between scalar and LVQ-based compression models at similar bitrates. Visually, the LVQ model produces sharper edges and fewer blocking artifacts, and also achieves a higher PSNR. Here's another example on a natural scene. Again, the LVQ-based model delivers better texture recovery and fewer blocking artifacts. To summarize, our adaptive LVQ framework enables both multirate and cross-domain neural image compression, with low complexity and strong empirical results. Thank you very much for your attention.